about stable oxygen, stable isotopes of oxygen. Remember last time we talked about absolute dating, and we mostly made reference to unstable or radioactive isotopes that decay at steady rate with excellent clocks for dating age of minerals or events in Earth history. Stable isotopes are excellent record of climate in past. So stable means they do not change. They get record at the time of their formation, and that record of time of their formation captures the ambient temperature. So if we are dealing with creatures that lived in surface ocean water, we can figure out what was the exact temperature of surface ocean water when we look at the oxygen isotope of foraminiferous shells. Oxygen comes in three natural isotopes. Oxygen 16, or light oxygen, is the most abundant type of oxygen atom in nature. There is about 99.77% of all oxygen atoms on our planet are this kind of oxygen. There is a very tiny amount of oxygen 17 isotope. Only about 3 10,000ths of oxygen atoms are oxygen 17. Slightly more abundant are heavy or oxygen 18 atoms. Rather than playing with these percentages and these small numbers, the much more simpler way to understand their relative ratio is if we multiply everything by 100, we will get these numbers. Out of 10,000 oxygen atoms, 9,977 are light oxygen isotopes. Only 3 are intermediate of oxygen 17, and 20 are oxygen 18 or heavy isotope. Because this one is so small, when we use oxygen isotopes, we look at the ratio of oxygen 18 versus oxygen 16, and that ratio tells us something about situation in the world ocean. Its temperature, its level, was it high sea level or low sea level? Because the temperature is reflection of the sea level too. So, ocean is major source of water on Earth. That's right, that's where a majority of water on Earth is stored. And there are mountains here. So we'll start from this diagram. When water evaporates, so knowing this idea that there are 3 varieties of oxygen, and there are also 3 varieties of hydrogen. Simple hydrogen, deuterium, or hydrogen that has 1 neutron in addition to 1 proton in its nucleus. And the heaviest of the 3 hydrogen isotopes, tritium that has two neutrons in addition to one proton in its nucleus, these three combinations of oxygen and hydrogen atoms make three types of water. Is that right? The most common is water made of light hydrogen and light oxygen. These other two possibilities are far less abundant. All right. So when water from the ocean starts its cycle, it starts with evaporation. That's right, water evaporates from the ocean. What type of water molecules are first to come out? I may not formulate this question. There is a water that's made of light hydrogen and light oxygen, oxygen 16. There is water that's made of this one, and we will neglect that oxygen 17 because it is just not playing any role in this, can only confuse you. Let's concentrate on light and heavy oxygen isotopes. So which of these two types of water is likely to evaporate easier from the ocean into the air?
The lighter one?
The lighter one. Why?
I'm guessing because it's lighter.
The good guess. It's lighter, it takes less energy to convert it from liquid to vapor state because it is less massive or takes less energy to kick it out from ocean. But some of the heavy oxygen water will also evaporate. Is that right? Because all water evaporates, but it is predominantly this lighter version of water that has lighter oxygen isotope involved. And when we get condensation of that water in clouds that start forming somewhere above ocean first, what we'll have? We'll have water that will predominantly be enriched in light oxygen isotopes versus heavy oxygen isotopes. Is that right? There will be much more vapor with oxygen 16 there than oxygen 18. Make sense? Okay. So we will just put this symbol oxygen. There will be more lighter oxygen in the clouds than heavy oxygen in the clouds. Now when we remove more lighter oxygen water from the ocean, what will be left in the ocean in respect of the ratio between oxygen 16 versus oxygen 18 water?
There'll be more oxygen 18.
There will be more oxygen 18 because more oxygen 16 left, is that right? So the ocean water will have the slight enrichment of oxygen 18 or heavy oxygen isotope water versus light oxygen isotope water. So that's the first step. Is that right? So these clouds start raining. When water condenses, which one will condense first? Light oxygen or heavy oxygen isotope? Heavy, why? Because it's heavier, it will fall. Just using the logic, it is heavier, therefore it will fall first because it's heavy. I'm using that logic. So, in some of the rain that will come out of these clouds, we will have heavier oxygen, water falling back to ocean, and the clouds will continue moving toward the land, now even more enriched in the lighter oxygen isotope than when the first rain started. Is that right? Because we squeezed out some of the heavy oxygen from these clouds, and now we have enrichment of lighter isotope further in clouds, and we have return of heavy isotope here and some more here, so that our ocean now gets progressively more heavy versus light isotope in it. Make sense so far? All right. There are many episodes of precipitation over the ocean before we eventually get to the land. When we get to the land, especially the high latitudes, where now precipitation comes mostly in forms of snow, we will have very enriched lighter oxygen isotope precipitation falling in these distant polar areas, and staying first before there's a snow predominantly, and stays as layers of ice that is now locked there. This ice will have mostly light oxygen water in it that is trapped in ice. Is that right? And heavy isotope will be significantly reduced in its average amount in respect to light oxygen isotope. So much that we sometimes reach up to 50, negative 50 per mil or per thousand parts of heavy oxygen isotope in respect to its relationship to light oxygen isotope. So A218 is now here very negative. Very little of the heavy oxygen isotope resides in ice. Tiny amounts, minuscule. This water does not return to ocean. You have question? Yeah.
The H2O 16 is the 50%, correct?
No, the H216 is overwhelming. It is almost 100%. 99 point something. Only tiny amount of water is made of heavy oxygen isotope. So that the relative amount of heavy oxygen isotope, which is usually somewhere around 0.1 or 1 parts per thousand, is now minus 50, so meaning that it is huge depletion of it. It should have been much higher concentration of it if everything is normal, but now it is telling us it is missing big time there, okay? We'll see why. since this water is locked, does not come back to ocean, general sea level drops because the evaporated water and we locked a lot of it on land without letting it return back to ocean. So when we have ice in large amounts in polar areas, global sea level will be low because some of this water does not return to ocean, stays on land, therefore causes drop in sea level. Because all this missing water is actually made of light oxygen isotope that is in ice, the lower sea level will be significantly enriched in delta O 18. So its values will be somewhere +2, +3, or even more per mils, because that tells us its concentration significantly increased in ocean because the light isotope is missing. It is not diluting this heavy isotope and giving it tiny amount. Now +3 means, whoa, there's extra oxygenating in ocean. Make sense? So it's not drastic like its negative value here, but it is way more than during the normal times when all water is back, during the warmer periods when all light oxygen returns, these values will drop to around 0 or below 0. Make sense? Okay. So the consequence of this, of cool global climate, is drop in sea level, increase in heavy oxygen isotope in water. So if during this time there is a foraminifera that swims in surface waters of ocean, it will take that water or oxygen from water to build its shell, which is made of calcite, so CaCO3. Parts of that CO3 will be derived from current water that will have these values of +2, +3, or sometimes +4 oxygen 18 versus oxygen 16 ratio that will have enriched values of heavy isotope in respect to light isotope. That forum will die, settle down, get buried, but it will always keep that ratio in its test. Then we go million or 50 million years after that, collect samples, we look at the depth, measure, we know what time that is, and we can say during this time 50 million years ago, see what the temperature was such and such because there is so much heavy oxygen isotope enrichment in seawater telling us global sea level was lower, surface temperatures were lower, therefore that's the indication of global climate. Make sense? So what happens during warm climate? We have same process. Lighter oxygen isotope will be prevalent in clouds because, again, it will be easier to evaporate lighter oxygen isotope than heavier. or you can see from that, okay? There you go. So we will have slight enrichment here of heavy over light isotope in early stages of the water cycle. Precipitation will again return mostly heavier oxygen isotope and slightly increase its amount, but eventually when it rains here, it is warm, all the water will eventually return back to the ocean and dilute the heavy oxygen that may start in enriching in early stages of water cycle evaporation, but eventually rain will come back, bring that lighter oxygen to ocean, and will have that small 0.2% of oxygen 18 value in respect to lighter oxygen isotope. So during warm intervals, when there is no ice on land, all the creatures that live at these times will have these depleted values of oxygen 18 or of heavy oxygen isotope, because they won't be showing any enrichment like they do during lower sea level and cooler global climate. Make sense? So, cold climate, lot of glaciers on land, enrichment in shells of foraminifera that reflect that global ocean was lower in level and had more oxygen 18 because oxygen 16 was stored in ice on land. If we go and pick up sample of ice from Antarctica or from Greenland and we find its concentration instead of -50, -30, that will tell us there was a warming interval that returned some of the lighter oxygen isotope back to ocean and reflects the warming trend in the long ice record in those areas. So ice has always very negative or depleted oxygen 18 values. The foraminifera has always enriched or higher oxygen 18 values during these cold periods in climate. Okay? So that's good essay question. What we do here, we use two standards for calculating these oxygen values because we need to make in respect to what? The first one is small, which stands for standard mean ocean water. So the standard mean ocean water is modern ocean, or ocean within the last 20, 30 years that has a little vial somewhere in Vienna that is kept as a standard that contains certain amount of this oxygen 16, oxygen 18 ratio that uses it as at this time in Earth history or climate, this was the standard. So anything that is different from this will tell us was it warmer or cooler than what it is today. Okay? The other one is PDB standard, which stands for PD formation, which is Cretaceous in age. B stands for belemnite. So there is a belemnite fossil that looks like a little bullet. You will learn belemnite later.
In the drawers you're looking for it.
Which drawer?
One of the, well, one's right before, nope, they're in front of you.
Here.
Yeah, they're in from the top view.
Belemnite.
Try top left. It's in one of the little boxes.
Hey, see? I told you, like a bullet. So this is belemnite. It's made of calcite. This is one of the few cephalopods made of calcite because most of them like aragonite. So this calcite has very unique value. Cretaceous was time of very hot climate. So this is a reflection of when global climate was very hot, when there was no glaciers on land, and this standard from belemnite of PD formation is another reference point. So when you find something that is similar in value to PD belemnite, that means it was hot global climate and no glaciers. If you find values that are less than that, means it was cooler than that time. So whenever you report stable oxygen values, you need to mention which reference are your data referring to. Is it expressed in reference to small or present seawater, or is it reference to PD belemnite concentration, which is Cretaceous time values of that oxygen value preserved in